So welcome everybody in the lecture hall, welcome everybody on Zoom, welcome everybody watching us from the future. Today I will continue, probably not finish, because again, there's a lot. Before that, I have questions for you, one question. So what is the key value in HBase? Or mostly, what index is it? So it's the smallest unit of physical storage. Is it indexed by columns and version and sharded by column families and time intervals? Or is it indexed by row and column and sharded by regions and column families? Or is it indexed by row, column, and version and sharded by regions and column families? Or is it indexed by row ID and sharded by regions? So I told you that key values are everywhere. So the notion of the key value model is absolutely everywhere. But in HBase, we write key values with a capital K and a capital V. So this is usually when you see it written in this way, it's the HBase key values. "42, that's a good number to end. So we have a majority right here, and the majority is in fact correct. So indeed, a key value, what's in the key, is the row, well, the row ID, the column, more specifically the column family and the column name, or qualifier, and the version, because I told you that on top of it, it's versioning the data, so it keeps multiple versions on the same cell stored in the background. So this is why you also have the version, and it is sharded indeed by regions, which are intervals of row IDs, right? And by column families. And when you have a region and a column family, the intersection of the two gives you a unit of where the H files basically are stored from. It's called a store, right? And so a store is just made of plenty of key values. Now I insist that key values are a physical thing in HBase. The users, when they interact with HBase, they see tables and rows and columns. But the key value, that's the physical thing that you actually store in the H files. All right. And basically, what's interesting is that the key value, the key has multiple dimensions. This is a bit different from key value stores. You remember in the key value store, the key is just a value. It's one dimensional, right? It's on a ring. There's only one dimension. One way to look at it, HBase, is a two-dimensional version of a key value store, meaning that now it has rows and columns. So now the objects are organized in a grid and not in a ring. And the other thing that key value stores don't have, and well, they kind of don't have, is the versioning. Let me say why. You do have versions in key value stores with the vector clocks, right? So this is meant for conflict resolution. But the difference is that in the key value store, the versions are organized in a DAG because you might have conflicts because of eventual consistency. But in HBase, the versions are in a total order. There is no DAG or anything, it's a total order. And the way you typically achieve a total order on the versions is with locks. If you have locks that prevent you from having any conflicts, then you have a timeline that is just a line. You don't have any DAG. For whom is that clear? All right. There's a lot of very general wisdom in what I'm telling you, right? The idea that when you have when you're not consistent, you have a DAG. When you're consistent, you have a line. This is a very general thing that you have in many, many database systems, not just HBase or what we are looking at. So let me get back to the slides. Okay. Is it not? Need to. Somehow I'm not able to click in advanced. Slightly reduce that so that I I basically need to be able to click here so that my clicker works, which is very weird, but this is the way it is. All right. So you remember this architecture, which is the same one as in HDFS with centralization, right? You have a coordinator node and you have the worker nodes. The HMaster is typically on the same node as the name node process. These are processes, and the region server process, these are also running on the same nodes as the data node processes. Now I owe you an answer, and Tobias found the answer to your question. You asked, what about the communication between the HMaster and the region servers? Are there heartbeats? The answer is there used to be heartbeats. In the earlier versions of HBase, it was heartbeats, just like in HDFS. Now, you might remember that I mentioned that in HDFS, the synchronization between the name node and the standby name node and the observer name node was handled by something called Zookeeper. Zookeeper, let me say a few words about that. Zookeeper solves the problem that in many of these systems, HDFS, HBase, MapReduce, and so on, it's a distributed system. So you have the problem that the nodes need to communicate together. The heartbeat is an example, like how do you keep track of all the nodes that are running? When you have the name node that fails, how do you synchronize on who is going to take over as the new name node, right? All of these things. And so in the first versions of all these systems, the developers implemented that by hand from the beginning. So in the first versions, they did not even implement it. And then you had race conditions, and then it just failed. You know what a race condition is, right? A race condition is when you have parallel processes, and then you have uncertainty of the order in which it gets executed. And then you get a wrong order, and then it crashes. So this is a race condition. You can have deadlocks, that the whole thing gets stuck, also because of race conditions. And basically, in the first versions, because the developers every time implemented it all over and all over and all over again, the way they implemented it was not perfect. So at some point, there was some people took action. They said, okay, let's do this right once and for all. Let us implement something that does it, and we fine-tune it to the point that it really, really works very nicely, and then everybody else can just use us. And that is Zookeeper. So Zookeeper is a very simple system that provides you synchronization, naming, grouping, and so on. So it allows everybody to have some coordination protocol. So this is the reason why the heartbeats in HBase were removed. And instead, HBase is using Zookeeper. And Zookeeper is just some distributed system where the region servers just declare themselves to Zookeeper and say, you know, I'm here. So they send the heartbeats to Zookeeper instead. And then the HMaster also looks into Zookeeper, which region servers are actually alive, right? And what is stored in Zookeeper doesn't take so much space, right? It's just a list of the region servers with some small data related to them, and that's it, right? So it's very, very small, and so that's why it's very lightweight. For whom does that make sense? Right. So no more heartbeats between region servers and the HMaster. And now a natural question we had with Tobias is what with heartbeats in HDFS? Will it be that in the next version of HDFS, they will also move to Zookeeper instead of the heartbeats? Maybe, who knows? We'll follow that and see if that happens too, right? All right, but you see what's interesting here is really the idea that when you see that many people do the same thing all over again and they do it imperfectly, then it's worth actually building one piece of software that does it really, really well and then have everybody use it, right? And I'll come back to this general principle. All right, so that answered the questions about the heartbeats. So now let me come back to where we stopped last time. So I was saying that if you look at one partition that is a region and a column family, the intersection of that, you persist it as HFiles to on HDFS, and I need to explain to you what there is in an HFile. So basically, I explained that these cells in here need to be serialized as sequences of bits, and every one of them is called a key value. And then the key values, I explained to you all the details of that. It's just a sequence of bits that has a variable size, but there is some magic so that you know exactly when they start and when they stop with the row length and the key length and so on. All right, so this is where I stopped. And then what I want to tell you now is that when you read key values to and from HFiles, you don't need one key value by itself. You read them in blocks. This is exactly the same idea as not reading individual bits from your hard drive, but reading them in these 4 kilobyte blocks. It's the same idea in HDFS that you don't read the files bit by bit, but you read them in HDFS blocks, right? 128 megabytes. And here we have HBase blocks that I call HBlock for the purpose of this course. So an HBlock has a size of 64 kilobytes. That is an HBlock. So you read key values in chunks of 64 kilobytes. This is an extensible block in the sense that unlike HDFS blocks and hard drive blocks that are an exact number of bits, so an HDFS block can be less than that, but not more than 128 megabytes. In an H block, you cannot cut a key value in half. You cannot cut in the middle of a key value. So it's very unlikely that the 64 kilobytes will exactly come where a key value stops. So instead, what you do is that you look at the last key value in the 64 kilobytes, but you still include it all the way to its end, right? So it might be actually larger than just 64 kilobytes, depending on the size of the last key value. For whom is that clear? Right? All right. So it's always a whole number of key values that you have in a block. And note that this is configurable. You can change that the H block size. That's entirely configurable. And note that if you put XML and JSON in there and you start having values that are like 10 megabytes, and of course that exceeds the size of an H block. And so that means that either you would have only one key value in your H block, which might be fine, or you can change the size of the H block. Do we have a question? Maybe I need to switch it on. Indeed. There you go.
Okay. If the key values are stored in HDFS, wouldn't you always have to get at least 128 megabytes at a time anyway? What's the benefit of retrieving less?
So that is a very good question. The way that it works is that when I talk about an H block like this, it's more logical than the HDFS block, right? So basically, the way to look at the H blocks, maybe I show you that slide and then come to your question because it will make it easier. So the idea is that when you look at inside an H file, it's basically a list of key values, but it has an extra index structure. So on the right, you have all of your key values. You can have a lot of them, right? And they are organized in these H blocks. So this is at least 64 kilobytes, 64 kilobytes, 64 kilobytes, 64 kilobytes, and so on, right? And so what you have in addition to these blocks, you have some index that is a way to accelerate the search for a specific H block. So you're looking for a specific key. You don't know where to look. You first look at the index that tells you what the boundaries are of the H blocks, right? And then, for example, you load that index in memory. It's also in the H file. You load it in memory, and then you look for key 14, for example. So you can very quickly see that it's between 11 and 17. So you know that it's going to be in this orange H block. So you just need to read this in order to open it, right? For whom does that make sense? All right. Now, all of this is an H file stored in HDFS. As a file stored in HDFS, it will be cut physically on HDFS in 122 megabyte blocks, HDFS blocks. What that means is that in an HDFS block, you will have a lot of H blocks, right? Who agrees? 64 kilobytes is much smaller, right? So you're going to have, you can do the division, in fact. It's 2,000, right? So you will roughly have 2,000 HBase blocks in an HDFS block, right? But you need to be careful because the HDFS blocks cut exactly at 128. So it might be that you even have an H block that is cut in half between two HDFS blocks because of that, right? Does it make sense? For whom is asking on Zoom? My answer is not done, right? But I just checking. Okay, checkpoint. Now something else that I want to say. Because you might wonder if anyway you're reading HDFS blocks 128 megabytes at a time, how is it even possible to just read 64 kilobytes, right? Can I read just 64 kilobytes of an HDFS block? And the answer here lies in remembering that I told you that if a region server is responsible for a very long time for the same region, at some point, there will be replicas of all the HDFS blocks on the same machine. You remember this, right? So that means that if the region server wants to read the HDFS blocks for an HFile, where are they? On the same machine. So it means that the region server might not even need to go to the name node or whatever to read anything. The region server is a process running on the same machine as the data node. It will directly read the blocks locally from the local hard drive. Who understands that? Okay, it's local, it's on the same machine. The HBlocks are basically locally stored on the same machine. And because they are stored on the same machine and you're just reading from a local drive, you know you have random access on a local drive, right? So because it's sitting on the same machine, it has these extra powers that it's able to just very efficiently read all of that data from the same machine. Okay, who is with me? I didn't see a lot of raise hands. Okay, very good. So this is the secret. So if you do have the data on the same machine, it's going to be fast. If you don't, then it's going to be a bit slower because then you need to fetch the HDFS blocks from somewhere else, right? So this there might be a performance penalty. Okay, does it help to know all that? Yep. All right. And I'm not even done explaining you. There's plenty more explanations that I will give you. Yes, we have another question over there.
So is this direct read from disk still using the HDFS interface, or is it circumventing HDFS overall?
It is so much circumventing it that it's called short-circuiting. It's literally short-circuiting the whole HDFS infrastructure and directly reading from disk.
Right, thanks.
So of course, the reason why it works is that the people who design HBase are part of the same team in Hadoop as those who design HDFS, right? Because otherwise it would be difficult to achieve that sort of things. But because it's all in the Hadoop project, then you can do that sort of things. Yes?
There's one already.
Yeah.
So do we have multiple H files per store or just one?
Multiple.
Okay.
And I will explain how. That I have to explain.
What's the criteria for choosing 64 kilobyte as a block size? Is this mostly for the index data structure or?
You mean the justification for that size? So it has to do with the fact, so it will be clearer after I explain what is coming next. But basically, this size of HDFS corresponds to what you will cache in memory. Because these HBlocks, in fact, will not every time be read from the local disk. They will also be kept in memory if they are used often. And so this is really the unit at which you cache the key values. And so the size of the HBlocks, so the HBase blocks, depends on your access patterns in HBase. For example, do you have a lot of queries that query just a few rows at a time? Then you would have you can use a smaller HBase block size. Or do you have very heavy queries that tend to read like 1,000 consecutive rows at the same time? If you have a lot of queries that read a lot of consecutive key values, then you can increase the HBase block size because that makes more sense, right? Then you keep them together and it's more efficient. So that really depends on the way you use HBase, the way you would configure the block size. This is the default value, 64 kilobytes, but you can change it depending on that, right? Okay. All right, let me continue. I will give a lot of things will become clearer once you have seen. Another question. What happens?
What happens if you want to change just one key value? Does it immediately need to modify the whole HDFS data node block?
That is a great question that brings me to what I'm going to say now. So this is awesome. So you're asking exactly the right questions. Perfect. So in an HFile, we have basically a list of key values sorted, ordered by key, plus an index that you can load in memory that allows you to find out which H block you need to look at if you're looking for a specific key value. Okay? And so this is why it goes faster. All right. Now I'm going to dive into the details. So let me have this overview of all the building blocks of the system physically. So we have the table. The table is this huge, big table with lots of rows and lots of columns. The tables are made of several regions. So that's the vertical partitioning, where you have intervals of row ID. So you might have thousands of regions in the same table. Within a region, you have the stores, as many as column families. So if you have 10 column families, then you are going to have 10 stores per region. Okay, so far so good. So the store is this wedding cake partitioning where you cut it both horizontally and vertically. Inside a store, we have multiple HFiles that hold the data for that store. And inside an HFile, we have the HBlocks. So an HFile is made of plenty of HBlocks. And the HBlocks are just lists of key values. Who is with me on this? Right? All right. So this is from the perspective of HBase, right? Because if you look at it from the perspective of HDFS, one level lower than that, then the HFile from the HDFS perspective is made of HDFS blocks of 128 megabytes, right? And so the HBlocks and the key values, you have to actually read the files to see them, right? They are inside the actual data of the HFile. Okay, so now here's the problem, and that's actually the question that was asked on Zoom, more or less. We can only write key values in sorted order. That has to do with the way HDFS works. If you write an HFile, the only thing you can do is write it or append to it, but you cannot modify an HFile in place. And thus the question on Zoom, how do I modify a key value if I cannot modify an HFile in place? Was it the question you asked? Reformulate it? Yes, exactly. And that's what I'm about to answer now. So we have the problem that we can only write like this, and they always need to be sorted. So how do we insert new values? And here's the answer. The idea is that we have on HDFS all of these HFiles for a given store, made of HBlocks, made of key values. And so the idea is that if you want to read HBase and you want to know the data because of a scan or because of a get or something, you in fact need to look at two places. You need to look at the HFiles and look for the key values in there. And you also need to look in memory. The reason is that the very fresh and recent key values that have just been added recently, they are stored in the memory. That's called the MemStore. So they are stored in the memory, and these are the older values. So basically, the idea is the HFile contain older values that have been persisted to HDFS, while the new and fresh values are still in memory. So the first element of answer to the question you ask is, if you want to insert a key value, or if somebody does a put with a key value, it just goes to memory. That's it. There's no HFile involved. It's just put in the MemStore, and that's it. Right? So this is the short answer to the question. But I will still need to answer how it makes its way all the way to the HFile later. Now, what I would add is that the MemStore needs to maintain a sorted order of the key values. With what data structure can you achieve this? You learned it in data structures and algorithms, right? What can I use to maintain in memory the order of key values? Yes? Binary tree. Exactly, a binary tree, or even more modern versions with multiple nodes per multiple values per node. That's exactly, so a tree structure. You can use a tree structure in order to hold the key values in order, right? So it means that anytime you insert a new key value, it takes a bit of algorithmic complexity to insert it into the tree. But the benefit is that when you look them up, then the lookup is logarithmic, right? So this is the benefit you get. All right. So every time you read key values, you need to check in the memory for if there's a fresh key value and in the on the disk for the older ones. What about writing? So if you write in the MemStore, right? So here's a new key value that just arrived because the user did a put, then another one, and then users keep writing. But at some point, the memory is going to be full, right? You have so many key values that it doesn't fit anymore. This is when you need to flush them to HDFS. So what's going to happen is called flushing. You basically flush the memory down to an HFile. Now, what's the algorithmic complexity of flushing these key values knowing that they need to be sorted? Who says n log n? Who says n linear? It is indeed linear. Why is it linear? It's already sorted, exactly. It's already sorted because I told you there is a tree structure, like your colleague answered. There is a tree structure there. And how do you traverse the tree structure? Just linearly. You go one by one through the already sorted key values. So you just need to flush them in the order in which you traverse the tree, nicely grouping them in HBlocks, 64 kilobytes at a time, building your index of the HBlocks so that they are easier to find and so on. So now the memory is empty and I have flushed its content to a new HFile. So now you see why these are the older ones, because now they are older than the new ones. But there is still a problem, because I told you we need a system that has to be resilient against crashes. So what if, before we had a chance to flush it to HDFS, that computer crashes and all the data that was in the memory is gone? What do we do about it, right? We need to make sure that we don't lose that data. Who agrees that we lose that if we just have the MemStore, right? If the node crashes, this is over. We lost the recent values. So what we do is that we use what's called a write-ahead log. A write-ahead log basically is a journal of all the transactions. It means that whenever somebody wants to insert a new key value or multiple new key values into the MemStore, before you do that, you put them in a file that's called an HLog, right? So the HLog is also a list of key values and of transactions of key values, but the difference between the HLog and the HFile is that the HFile is sorted by key, right? It's sorted by key, but the HLog is sorted by the time of arrival. It's really a journal, and you keep appending in the order in which they arrive. And we know that appending in HDFS is fine. We can append without any problem. So this is why the HLog gets continuously appended with new transactions that arrive. And only after you have appended to the HLog are you allowed to write to the memory store. So now if it crashes, that's okay because we have the HLog, right? So of course, what happens if you want to recover from the crash is that you will need to go through the HLog and apply the changes. That might take a bit of time, but at least you didn't lose the data. Note that the HLog here is very similar to the edit log in the name node of HDFS, where you have the order in which you modified the file namespace. Do you remember the edit log? Right? It's exactly the same logic. So it is just, in case we crash, we kept a journal somewhere, and if it crashes, we use that journal to recreate and recover all the data that we lost, okay? There is one HLog for each region server, right? So everyone has an HLog, and it is on HDFS. All right, and then once it's in the HLog, we can put it in the memory. All right, so when do we flush? Well, when the memory is full. What does it mean? It could be that in a given store, you reach the maximum size. It could be that the total MemStore of the entire cluster reaches a critical size. So you basically start fearing that if it crashes, that's going to take a long time to recover. So you just trigger a flush as well. So it's an overall flush, then you flush everything. Or you could also flush if the write-ahead log is too full, right? If the size of the HLog is too full, then you also trigger a flush. By the way, the write-ahead log and HLog, that's the same thing, right? HLog would be the name of the actual file structure on HDFS, and write-ahead log, or WAL, you might see, is the concept. The concept of the write-ahead log is not unique to HBase. This is in many, many different systems that have a similar issue and need to be resilient against crashes. Okay. So now that we know that the fresh values are in the memory, and when it's full, we flush it to an HFile, we can go into reading them. Another question?
I have a question about writing. So when we flush the memory store in the H files, do we create a new HDFS block for this H file, or do we interact directly with the local memory and write in a still non-full HDFS block?
So the first thing that I would say is that the H file might be very large. It might be a terabyte, you know, hundreds of gigabytes or a terabyte. So it means that the H file that you see here might consist of many, many HDFS blocks, right? So not just one, but many, many HDFS blocks. Now, when you write the H file to HDFS, it is written like anybody else would write a file to HDFS. You go to the name node, you say, I would like to write a file to HDFS. The name node answers with the locations for the first HDFS block. Then you write, then you ask for a second block, and so on. So the way you read the H file, you write the H file, has really nothing special. You just write it the normal way you write to HDFS. And that does mean that as you go through the key values and create the H blocks, at some point you will finish an HDFS block, then you just trigger a second HDFS block, and so on and so on. And you might end up writing hundreds of HDFS blocks that each contain 2,000 H blocks or something, right? That's the idea. Does it make sense? Yeah? Then we have a question on Zoom, I think. So it's another marathon, right? Tobias is running a marathon. That's very impressive for the first time, right? Yeah.
When we talk about storing this in memory instead of an H file at first, do we mean it's still stored on a region server in memory, or is it stored somewhere else?
It is sorted in the memory. So it's really a tree structure in the memory of the machine on which the region server is running. Yep. Right, more questions? Okay. So now we know we flush. So let's think a little bit how we read the data now. If somebody would like to look for specific key values, they will need to check everywhere. So the region server, more exactly, will need to check everywhere. So the region server needs to look in its memory, if perhaps there are some key values that are searched by the user, and in every single H file. Now, of course, because of the index with the H blocks, it's going to be a bit easier to find the key values in every H file because it's all sorted, you know, by key. But you still need to do it for every H file and for the memory. So far, so good? Everywhere. Now, let's imagine that the memory is becoming full, we flush, then it's full again, we flush, then it's full again, we flush. Well, at some point, we're going to have a lot of H files, right? That start accumulating dangerously on HDFS. So now you can imagine if I have a lot of H files, then it's going to become slower and slower and slower when I have to serve a request, because then I have to check even more H files now, right? So we cannot just let it go like this forever, creating new H files, right? So what do? We compact. So what we do when we have too many H files is that we merge them into a single bigger H file that has everything sorted. What is the algorithmic complexity of that? Yes? Linear, exactly. And why is it linear and not n log n? Exactly. It's basically the second part of the merge sort. Remember the merge sort? It's one of the algorithms for sorting. This is the second part of the merge sort. So basically, you just need to traverse the H files in parallel, and that is linear. And as you traverse them in parallel, you write and always put the smallest remaining key value in there. So this is linear, very highly efficient. This is called the compaction, right? Flushing means from the memory to the H files. And compacting H files is also linear. This is taking multiple H files and writing the next H file. Note that you can stream. You can do that in a streaming fashion. It means you don't need to put the entire data in memory to do that. You can really do it just with pointers on the next key values in each file, and that's it. And then you forget the key values you've already written. So you can even do that if the size of the H file is larger than the memory. That's not a problem at all. Who sees that? Right? It's just like watching Netflix, but instead of a great series, you just go through key values. Okay. Now, there is some way that we do the flushing and the compacting. It's not just a mess or random way of doing flushing and compacting. There is actually a pattern. And this pattern is in fact called LSM-trees, log-structured merge trees. And the LSM-trees are usually associated with the cases where you are throughput bounded. That's exactly the case with HDFS. I said that the bottleneck is the throughput. We want to emphasize the very high throughput, and we don't care about the latency. So this is the case where we will be using the structure that I'm about to show to you, as opposed to B+ trees that you might have heard in the context of relational databases. Who's already seen a B+ tree? All right, I know that everybody in information retrieval has, and I think if you had a bachelor level relational database lecture, you probably saw them as well. The B+ trees are popular in relational database management systems because they are really great for low latency, right? It's indices, you can index your data in a database. So when you're optimized for low latency, you can use B+ trees. When you're optimized for high throughput, you can use LSM trees. That's just the intuition. I have to tell you what's an LSM tree. Log-structured merge tree. So the idea of a log-structured merge tree is that you have multiple levels of data storage. The top level is the actual working memory. That's the MemStore. The next level is what you have flushed to HDFS, right? So that's what got flushed from the memory, level 1. The next level is what has been compacted out of this one. So you flush and you compact, and there can be even more level because you might even compact and compact again, right? And they grow even larger and larger. So this is what the log-structured merge tree is, right? And again, imagine this is the MemStore. This is when you flush, and this is when you compact. Now I have an animation for you. Who knows about the 2048 game? Who already played it? Who already won it? Oh, wow. I never managed. I need to try more. All right, so what's about to happen is exactly like the 2048 game. So if you have this pattern in mind, that should be easy to understand. Is there a question? Yeah, no, right. So let me continue. Let's see, we fill the MemStore. What happens? We flush to an H file. Now the MemStore is full again, so we flush again. Yeah, so now we get a second H file. Now, 2048, I have two H files. So I merge them, they have the same size, I merge them to a larger H file. Now the MemStore is full again. I have another flush to an H file. This is in the 2048 game where the 2 appears again and again and again and again at every turn. So the 2 is basically this little H file here. Then I have again a flush, second H file, I compact them, get a 4. Now I have a 4 and a 4, so I get an 8. You see, that's the idea. So I basically keep merging and merging and merging. Every time I have 2 H files of the same size, I merge them again. Then I flush again, that's again a 2. I flush again, that's another 2. Then I compact them, get a 4. I flush again, and so on. In fact, if you look closer, you're basically counting in base 2. Just it's a mirror of the base 2. So this is, I'm rewinding, this is 1. This is 1, 0. This is 1, 1. This is, this is 1, 1. This is 1, 0, 0. this is 101, this is 110, and this is 111. Okay, so we are counting in base 2, and that's exactly like the 2048 game. Who sees it? Okay, so that's it. That is the log-structured merge tree. Now, I did it in base 2, but it doesn't need to be in base 2. You can also do it in base 3, in base 4, with more HFiles until you compact them, right? And so what's going to happen in the structure is that the very, very recent key values, they are in the working memory of the computer. The slightly older values are in here. The even older values are in here, and the even older values are in here. So the older the values, the larger the HFiles. Now, it's good because those who had information retrieval also saw that, because that actually is also used in information retrieval for some indices. So that's exactly the same LSM tree that you've seen in information retrieval. Yeah. I even joked that, like to joke that if you go with the very, very large HFiles, you might even find dinosaur fossils, because this is the oldest data. All right. Any questions on Zoom? Okay. Who is comfortable with the material, has the feeling they understand what's going on? Okay, very good. I told you it's the toughest of all lectures. So if you can follow that, then this is good.
Now there's a question. Is this similar to the memory cache structure?
I'm not very familiar with memory cache. Do you mean in general the way caches are implemented?
I would say yes.
I wouldn't know. I'm really sorry. I don't know about memory caches. We could, but that's homework for us. I mean, we could take a look. Maybe you can send us a message and with more details about the question, and we'll investigate. Yeah. I warned you, I don't know everything, right? Yes?
Like updating key values, but here we saw like writing new HFiles. So we haven't really seen updating key values yet.
Yep, so let me answer that. So I'm going to rewrite. So the question is, you didn't have a microphone, right? So the question is, I showed you when you create new key values, what about updating a key value? The idea is that in order to update a key value, you in fact insert a key value, because we have a versioning system, just like Git. So it means that if you want to update the value that is in a cell somewhere, all you need to do is create a new key value with the version +1. So basically, even modifying a value consists in adding key values to the memory store. And what's going to happen when you read from all of these places, where is it? Yeah, when you read from all of these places, what happens is that you get all the key values that the user is looking for, and you will get key values with multiple versions. You just take the latest. So all the key values that have the latest version, you give them to the user. All of those that do not have the latest version, you just skip them, you hide them. If the user wants to see the older value, then they can. In the API, they can explicitly request an older version, but by default, you just return the latest version, right? And so this idea that updating really means inserting is very common to all the systems that are like this, with consistency and a timeline of versions, right? Does it answer your question? Yeah, all right. And on Zoom?
So about the versions, do we get rid of them at some point?
Yes, you can actually get rid of versions. In fact, you do get rid of versions. When can you do it? When you flush and when you compact. So if you look here, when you flush, you go through in order through the key values that are in your MemStore. So since they are in order, all of those that are the versions of the same cell will be together. That is the perfect moment to drop some of the older versions and to prune a little bit, so that what you actually write on the HFile can be a bit less. The same goes when you compact. So when you compact like here, you can also, because you traverse in order by key, you can also prune the older versions. So every flush and every compaction is a great opportunity to get rid of older versions, right? Which brings us to the end of the lecture. Thank you for participating and asking so many questions. We'll continue next week at 2 p.m. The usual. So enjoy the exercise session. Thank you very much.